One of the key components for building machine learning systems is data, and that data typically takes a specific format. In a supervised dataset, we have both the features and the labels for every example. The label is the thing that we want to predict, and the features are the things that we want to predict the label from. We often call the label the target, and in an unsupervised dataset, we only have features and no labels. But everything I'll mention about features still applies to unsupervised or supervised datasets. Common example, you're going to predict how many of a product that you're going to sell if you put them up for a particular price. That's the pricing problem. In that case, you might have a data set of products and their details, and the previous price could be the features, and the number of them which were sold previously could be the labels. So you've got this data set of features and labels of examples which you've seen in the past. Now, what you want to do is use those examples to try and build a new system that can predict how many of them are going to sell at a particular price for new products when you have their details and their price, but you don't have the label yet. We typically call the features X and the labels Y. And each of these is essentially a list of features or labels for each example. So here I've got drawn an example of features. This is example I. The I is just the index for that particular example. And typically we refer to the total number of examples in a dataset as M. So it'll go from X1 to XM. And here you can see that each of the examples has a number of different features. It's got N different features. So this here, that's feature 2 for example I. The subscript is the index of the feature that I'm talking about, and the superscript is the index of the example which I'm talking about. If you just got one feature, then you can picture it at somewhere along a number line. If you got 2, then you can picture the features in a 2D feature space. And if you've got 3, well then you can picture them in 3D space. But of course you can have many more features. You can have as many features as you want. And the generalization of that is just a vector of n dimensions. And the machine learning problem is basically to do this. It's to take some features in feature space and find a way to map them to the label space. So how can we squash and stretch this space over here so that everything ends up in this space over here in the right position, where the input features are mapped from the feature space onto the right place where the target sits in the label space. And really these feature space and label space, they can be any shape or size that you want. You could have 1,000 input features. You'd have way more than that if you're dealing with images or videos, and you could have multiple labels per example. The typical case is that each example has multiple features and a single label. And that's why here I've drawn the X capitalized and the Y lowercase, because the X is a matrix and the Y is a vector. And the X is a matrix here because it contains all of the examples and all of their features. So I've got M different examples, that's how many rows I've got in this matrix, and I've got N different features, that's how many features I've got in each example. So overall, I get an M by N matrix. And we call this the design matrix. It contains all of the features which I want to make predictions from. And then I've got a corresponding label vector, which has labels for each of those examples. So it's M labels long. And in this case, I've just got a single target for each example. But you could also have problems with single examples or multiple labels or any combination of those things. In the simplest case, the features are numbers and the target is a single number. For example, if you're predicting the price per night of a new property uploaded to your app from the features which are the number of rooms and the area of the floor space. 2 features, both numerical, you're predicting the price, which is also a number. That's a very simple case. But the features and the labels can take any format. For example, the input features might be an image or a video or text that you want to make some prediction about. And commonly the output is also formatted as a classification. Specifically, it might be a distribution of probabilities over the different possible output classes. So you could have any of those kind of combinations mixed in, all those different kinds of data, all those different kind of outputs that could be, classifications or whatever else. But whatever the data format, it's important to note that the first dimension is always what we call the batch dimension. So what I've shown here in the design matrix, the first dimension is this number of rows. And that's the batch dimension here. It shows how many examples are in this batch. And along that dimension is every example in the dataset. So let me give some more examples of how you would format your data for different typical machine learning problems. Object detection is a problem where you try to predict a bounding box around a specific object in an image. And in that case, you have an image as input data and multiple labels. You have to predict the height, the width, and the X and Y coordinates of the center of the box. And that example could easily be extended to video detection too, where you have bounding box predictions for every frame. Another example would be recommendation systems. And a simple way to set that up would be you have a table which shows the user and the movies that they watched for all the users in your history. And then you have a new user example which has some characteristics about them, and you want to predict whether they're going to watch this movie or not. There are a number of different ways that you could tackle any of these problems, but the point here is that almost any kind of problem can be framed as a mapping between numerical features and numerical targets. And there's always a way to represent the data in this format, although some types of data can be harder to format than others. So notably, text data is not numerical, but there are ways that you can transform it into a numerical representation. And an example of where you might want to do that would be things like text auto-completion. In that case, your dataset would be a load of text examples, and the features would be text up to a certain point, and the labels would be the complete text. And this makes what's called a self-supervised dataset, where the text itself is both the features and the labels. But to do that, to format the text into numerical format, it requires some more complex transformations that I won't get into here. So stay tuned and you'll learn how to do that.